Welcome back to the Deep Dive. Today, we're charting a course through sustainable architecture in 2025. And, well, what our sources show is this isn't some niche interest anymore.
Not at all.
It's really become a core global imperative. I mean, the numbers are pretty stark. Something like 67% of industry stakeholders are familiar with these ideas now.
And even more, 69% actually prioritize sustainability in their projects. It's a huge shift.
It really is. It's not just about cutting emissions, is it? It feels like we're fundamentally reshaping how we think about the built world.
Absolutely. And our mission today really is to give you a kind of shortcut to understanding this transformation. We're going to look at the big global design ideas first, the sort of philosophical underpinnings.
Okay.
Then we'll zoom right into the innovative materials making it possible. And finally, contrast those global trends with what's happening regionally, specifically looking at places like Nepal and India.
Mm-hmm.
The idea is to provide a holistic picture of this whole decarbonized built environment.
And it's crucial, isn't it, that the word sustainable itself has broadened out so much? It's moved way past just, ticking boxes for energy or water saving.
Definitely. It's now about the entire life cycle.
Right, integrating human health, real social benefits, and importantly, economic value, too. You see it in the big certifications like ED and BREEAM. They now have specific sections just for health and well-being.
Indoor environmental quality.
Yeah.
Yeah. The building has to work for the people inside it, too, not just for the planet.
Okay, so let's unpack that. When architects kick off a project now, the strategy seems to start with, working with nature and designing out waste from the get-go. Passive design first, right?
That's the bedrock. The fabric first principle. Before you even think about fancy mechanical systems, you optimize the building itself, its shell, its orientation.
How so?
Well, you prioritize careful site analysis. Where does the sun hit? How can we maximize natural ventilation? Good shading. You get the building envelope right first.
So you're minimizing the load on things like heating and cooling right from the start.
Exactly. By using things like parametric studies early on, you can really reduce how much mechanical equipment you even need.
And does that initial thinking actually save money?
Oh, significantly. By tackling the fabric first, firms can cut both the initial building cost, the CapEx, and the long-term running costs, the OpEx. We're talking potentially 20 to 30% savings over the building's life.
Wow, that's substantial. That ties directly into biophilic design too, doesn't it? Bringing nature into the building.
Yeah.
How does focusing on natural light or green spaces go beyond just saving energy?
That's such a critical point. Integrating nature, whether it's just maximizing daylight or using green roofs and walls, yes, it cuts energy loads.
Sure.
But it also fundamentally boosts occupant well-being. The data shows it reduces stress. It can increase productivity by, up to 15%.
15%? That's quite a jump.
It is. And functionally, take green roofs, they can slash a building's cooling needs by around 70% in some climates, just by using nature effectively.
70% is huge.
It is. So if that passive efficiency is the foundation, the next big shift in thinking comes with the circular economy. We're really trying to move away from that old linear model. Take resources, make something, then throw it away.
Right, the take, make, waste idea.
Exactly. The new thinking is to see buildings not as disposable things, but as material banks.
Material banks. So everything inside could potentially be used again. What does that mean for how you actually build it?
It leads straight to something called design for disassembly, DFD. You have to actually engineer the building so that components like beams, panels, even mechanical systems can be easily taken apart, recovered, and reused later on.
So you're planning for the end of life right at the beginning.
Precisely. And the most obvious application right now is adaptive reuse, taking old buildings like Oakland's Uptown Station and transforming them instead of tearing them down.
That avoids all the carbon involved in making new materials, I assume.
Exactly. You avoid that huge embodied carbon hit of new construction. Retrofitting can save up to 50% of the carbon compared to demolishing and building new. It's just smart resource management.
It's fascinating, designing for the future, not just the present. Now, another concept that sounds almost sci-fi is biomimicry, using nature's designs as a blueprint. It sounds complex, but maybe sometimes the best ideas are simpler.
They often are. I mean, look at the Eastgate Center in Zimbabwe. It's a famous example. Its ventilation system was modeled directly on how African termite mounds keep themselves cool.
Termite mounds, really?
Yes. No conventional air conditioning at all. It relies purely on natural convection currents and the building's thermal mass, just like the termites do.
Okay, so what was the result? Building a skyscraper like a bug's nest. Did it work?
Phenomenally well. It uses about 90% less energy for climate control compared to a similar-sized conventional building in that climate. 90%.
Incredible.
It really proves that sometimes, yeah, the most advanced engineering solutions have been around for millions of years.
So if the design philosophies are about efficiency and circularity, the pressure then falls on the actual materials we use, right? Construction's carbon footprint is huge, largely from cement.
It is. Cement production is a massive global emitter. So the focus now is squarely on developing and using low-embodied carbon materials.
Which means we have to tackle the biggest one, concrete.
Precisely. And we're seeing kind of three big waves of innovation there. First, there's self-healing concrete.
Self-healing, how does that work?
It's engineered with these embedded agents, sometimes bacteria, sometimes polymers that get activated by water or air if a microcrack forms.
Yeah.
They then react and, well, essentially repair the crack autonomously, often within 24 hours.
That sounds potentially expensive. Is that something we're likely to see widely used soon, or is it still more experimental?
It's definitely emerging. The initial cost might be higher, yes,
Yeah.
but the idea is the long-term value. If you extend the building's lifespan significantly, you reduce its overall environmental impact over decades.
Right, the life cycle perspective again.
Exactly. But maybe more immediately impactful for mass adoption are the other two innovations. First, supplementary cementitious materials, or SCMs.
SCMs.
Yeah, it means replacing a big chunk of the traditional cement, the really carbon-intensive part called clinker, with industrial byproducts. Things like fly ash from coal plants or a slag from steel making, GGBFS.
So using waste from other industries.
Exactly. It dramatically lowers the carbon footprint, and often these materials actually improve the concrete's strength and durability too. And the third area is carbon-capturing concrete.
Capturing carbon? How?
These are materials actually designed to absorb CO from the atmosphere as they cure and harden. They essentially lock the carbon into the concrete itself, potentially making the material carbon negative.
Wow. Okay, beyond concrete, we're also hearing a lot about materials that are either grown or just renewed very quickly. Things like hempcrete.
Right. Hempcrete is fascinating. Carbon negative because the hemp absorbs so much CO as it grows, and it's also fire resistant. Then you have mycelium composites.
Grown from fungi.
Yeah, basically mushroom roots, bonded together to make panels or blocks. Fire resistant, biodegradable, and of course engineered bamboo for structural uses. The focus is all on rapid regrowth and recyclability.
And underpinning all this material science is technology, I guess, making the whole process smarter.
Absolutely. Digital tools are transforming design and construction. AI, for instance, can now analyze countless variations of a floor plan or simulate energy use in incredible detail, helping to catch potential design errors, maybe up to 40% fewer errors before you even start building.
That precision must feed into how things are actually built, too, like with prefabrication.
Directly. Knowing exactly what's needed allows for much more efficient off-site modular construction. Building components in a factory environment cuts down on-site waste dramatically, maybe by 30%, and it really speeds up the construction timeline.
So digital design enables better factory production.
It creates that seamless link, yeah. Design optimization feeding directly into efficient execution. Okay, so that brings us to a really interesting point. How do these big global ideas actually play out on the ground? When they meet specific regional needs and contexts, let's take a look at South Asia, specifically Nepal and India, where you see this fascinating blend of high-tech policy and, well, really deep-rooted local wisdom.
Okay, starting with Nepal. The context there is obviously shaped by the seismic risk, especially after the devastating 2015 earthquake. So resilience must be key, alongside affordability and cultural fit.
Exactly right. And that necessity has actually sparked this really powerful revival of traditional vernacular building techniques. We're seeing a big push for rammed earth construction and timber-framed houses again.
Why those specifically?
Because they're being promoted as both eco-friendly using local materials and more resilient to earthquakes compared to some of the unregulated concrete structures that had become common. They rely heavily on local stone, mud, and bamboo, which grows quickly there.
So it sounds like the circular economy isn't just a fancy concept there, it's almost a necessity.
It really is, driven by practicality. There's a huge emphasis on upcycling materials, salvaging stone and wood from damaged or older buildings. Because dealing with concrete waste is difficult and expensive in that region, there's a strong preference for materials that can basically just return to the earth naturally when they're no longer needed, minimizing hard-to-recycle waste.
Makes sense. India, though, seems like a different picture, a huge scale, blending ancient practices with very modern top-down policies.
India is a fascinating case study in this blend. They're consciously taking traditional bioclimatic design principles, things that have been used for centuries, like internal courtyards for airflow, high ceilings, using jallies or screened openings for shade and ventilation.
Right, passive cooling techniques.
Exactly. And they're formally integrating these alongside modern green building standards like GRIHA, which is India's own rating system, and LEED India.
How does that mix show up in the materials they use?
Well, they still widely use traditional regional materials like laterite stone or mud bricks. But they're also major adopters of innovative recycled materials, especially things like fly ash bricks on a massive scale, using up that industrial byproduct we mentioned earlier.
And the government is pushing this.
Very actively. There are strong policy mandates driving tech adoption, things like mandatory rooftop solar installations on new buildings in many areas, and very specific rules around water conservation. Rajasthan, for instance, just brought in a rule in 2024 requiring rainwater harvesting systems for all new large buildings. It's policy-driven innovation meeting tradition.
Okay, so we've covered the philosophy, the materials, the regional adaptations. Let's talk economics. What does this all mean for the bottom line? The business case seems strong on paper, but adoption still feels patchy sometimes.
Well, the financial data is compelling when you look at it. Green buildings consistently show significant energy savings, often in the 25% to 50% range.
That's considerable.
It is. And they tend to command higher market value, 2, maybe 7% higher on average, and achieve higher rental rates, around 6% more than conventional buildings. Plus, you have the human factor.
Better air quality, better light.
Yeah, leading to increased occupant productivity. Some studies suggest boosts of up to 20%. So the overall financial picture, including operational savings and value uplift, is incredibly strong.
But if the numbers are that good, why isn't every new building sustainable? What's the main barrier holding things back?
It nearly always comes down to the perception of high upfront costs. That initial investment figure tends to overshadow the documented long-term savings and value.
But is that perception actually accurate? Are they always more expensive to build initially?
That's the critical point. Often, they're not significantly more expensive. Research shows that the construction costs can be comparable, or maybe only slightly higher for really advanced systems. The real issue is that the industry, and particularly the finance side, tends to rely on very short-term financial models.
Looking only at the build cost, not the running costs.
Exactly. Instead of embracing life cycle cost analysis, LCCA, which looks at the total cost over the building's entire lifespan, we often get stuck on that day one price tag. It's a mindset issue as much as a cost issue.
And that's where standardizing things through certifications like LEED and BREEAM becomes so important, right? To quantify that long-term value. How do those two main systems compare, briefly?
They're both crucial for driving standards globally. LEED, which originated in the U.S. and is dominant in North America, primarily relies on reviewing documentation submitted online to award its different levels: certified, silver, gold, platinum.
Okay.
BREEAM, which is older and widely used internationally in over 90 countries, has a key difference. It mandates on-site verification. Independent licensed assessors had to physically inspect the building to confirm its performance against the criteria for its star ratings, from pass up to outstanding.
So one is more about documented design intent. The other adds mandatory real-world checks.
Broadly speaking, yes. Both play a vital role in pushing the market forward and providing that standardized measure of performance.
Well, this has been a fascinating deep dive. To try and sum it up, it feels like sustainable architecture, now, in 2025, is really defined by this convergence, pulling together the circular economy, smart passive design, and ideas borrowed from nature. It's a truly holistic systems approach.
Absolutely. It considers the planet, the people, and the economics together. And looking just slightly ahead, the next big layer being integrated is resilience.
Resilience against what?
Against the impacts of climate change we're already seeing. The industry is rapidly working to integrate climate adaptation. Measures things like better flood-proofing, designing fire-resistant building envelopes, tackling extreme heat directly into sustainable design frameworks. The goal isn't just efficiency anymore, it's survivability too.
Building structures that can actually withstand the increasing environmental stresses.
Precisely.
Okay, so we've seen the amazing potential of materials like self-healing concrete and the proven success of just copying nature with biomimicry. If, as you said, the perception of high upfront cost is still the single biggest hurdle. And yet the long-term financial returns are clearly there when you use life cycle cost analysis. What kind of creative policy or maybe financial incentive could really shift the industry's focus? How do we get developers and investors to prioritize that LCCA model over short-term cost thinking and truly unlock sustainable construction's full global potential?
That's the million-dollar question, isn't it? Or maybe the trillion-dollar question for the global economy. Finding that lever is key.